So this video is about a method of solving systems of equations by substitution. Now when you solve systems of equations, what that means is we're trying to find a solution to two or more equations. Usually it's two equations. And so we've talked about different ways to do that. One of the ways is to graph the lines and see where they intersect. And there's some advantages and disadvantages to graphing. So today we're going to use another method, which is called substitution. Substitution is very mathematical. It's a lot of equation solving. But what's valuable about substitution is it'll work for any equations that you have. Sometimes it's difficult to graph them and get an accurate answer, but with substitution, you can get an answer every time. So here's an example from our textbook, question number 11. X plus y equals 8 and y equals 3x. And remember, what we're trying to do is find the solution to both of these equations. Each equation by itself has an infinite number of solutions, x, y pairs that are graphed on this line. And if you plug those x, y coordinates in, they'll make this sentence true. But usually there's only one solution that's true for both lines. And if you graph the lines, it would be the point where they intersect. So here's a different way to find that by substitution. When you look at substitution, you try to find out the smartest way to do it, the most efficient way. And so what I want to do is I want to find out one of these equations has a variable by itself. In this case, the second equation has y by itself. So I know that the value of y is equal to 3 times the value of x, or y is worth 3 x's. So what that allows me to do is replace the y in the top equation with its value of 3x. So here's what I would do. I would rewrite this equation as x plus y, but instead of y, I'm going to use y's value because these two are equal. So I can substitute them without changing it. Just like I could turn a $10 bill into 2 $5 bills and they'd have the same value. So that equals, in my equation on top, equals 8. What I've done is I've eliminated one of the variables, so now I can solve for the other variable. In this case, I'm going to solve for x. So 3x and x makes 4x, and 4x now equals 8. They've combined like terms. If I divide both sides by 4, then I get a value of x equals 2. So now I know my x value, but I don't yet know my y value. So since I used the first equation the first time to find x, I'm going to use the second equation to find y. So I would put in y equals 3, and then again I'm going to substitute the value that I found for x. I found that x was worth 2. So I'm going to substitute a 2 here. This is a pretty simple example. I end up getting y equals 6. So my solution is the ordered pair 2, 6. My x coordinate and then my y coordinate. Now before I leave this problem, I want to make sure that it works in both equations. So I'm going to check it by plugging it into both. So my first equation is x plus y equals 8. So that I put my x value in and my y value in. We evaluate both sides. They're equal. So I found a solution to that equation. If I put the x, y coordinate in, that sentence is true. Now let me check the other equation. Y equals 3 times x. So my y value is 6. My x value is 2. And since both sides are equal, once again I found the solution to that line. So since this ordered pair is graphed on both of these lines, it is the one point that is graphed on both. It's the intersecting point. It's a solution to this system of equations. So now we'll do another example from the book, number 15. It's a little bit more complicated. So you see the equations there, y equals negative 2x plus 6, and 3y minus x plus 3 equals 0. Now sometimes I like to make them both in the slope-intercept form to make them a little simpler, but I'm not going to this time. Because this time I have the first equation where y is by itself, so I know what y is worth. So what I'm going to do is I'm going to take this equation and I'm going to substitute the value of y in that equation into the second equation. So I write the second equation it'd be 3 times y. Now y is worth negative 2x plus 6. Okay, so that's the 3 times the y. Then I've got to subtract x, add 3, and that equals 0. So now I've got to distribute this 3, and I get negative 6x plus 18. Then I've still got to subtract x and add 3 to equal 0. I got kind of a complicated stuff over here, but I've got one variable. I've only got x. So now I combine like terms. And if I combine a negative 6x, subtract x, I get negative 7x. And if I take an 18 and a 3, I get 21. Still equals 0. Now to get x by itself, I'm going to subtract 21 from both sides. So I get negative 7x equals negative 21. I want to divide by negative 7 on both sides. And x equals 3. So now I found the value of one variable. So if I take this value and I substitute 3 every time I see x in this equation, what that does is it eliminates x from that equation, so now I can only solve for y's, which is the missing variable I have. So I get y equals negative 6 plus 6, which is 0. So now I believe my ordered pair is 3, 0. And of course I want to check that in both equations. So let me go to the first equation. Oops. I don't want to put y there, I want to put what it's worth, which is 0, equals negative 2 times 3 plus 6. I want to evaluate both sides. Okay, so it's true for that equation. Now I'll go to the second equation, which is a little bit more complicated. And I want to put 3 times y, now my y value is 0, minus my x value, which is 3, plus 3, and that needs to equal 0. So this will be 0 minus 3 plus 3 equals 0. So this will be, don't need the 0, so negative 3 plus 3 is 0, and 0 equals 0. So this xy coordinate works in both equations. So I found the solution to that system of equations.